In the next few videos, I'm going to walk you through two documents. The first one is the IC SLE 442 document and the contact reader writer ACR 39X document as well. So I'm going to point out and make you understand some of the important points in these two documents. So you can always download this from internet, either from the manufacturer site, or you can go to this ACR 39 website and download the reference manual. First we are going to go through the chip card and see how this chip card has been programmed using the ACR 39X. So I'm just going through scroll through page by page, and where there is any important data I'm going to stop and we are going to discuss as well. So in the page number 7, what we see here is there are two types of SLE 44 series chipset. One is the 32 and other is the 4442, and the difference between these two is the 4442 supports the password, whereas the first one looks like it has no password protection, so you can read and write anywhere in the memory. So I myself haven't come across this chipset, so I will not go through that. So as the document says, some of the important features are it has got 256 bytes of EEPROM, and it is byte-wise addressing. So this means every byte you can address and you can read and write. It has got irreversible write protection bits, and this is only for the lower 32 bytes, and each of these lower 32 byte is controlled by a 32-bit protection memory. So this is based on two-wire link protocol, and all the other bits there are some of the important features of the chips which is not required for programming. So as you can see here, this mentions about the 4442, which says it has got a 3-byte passcode, so which you have seen in the previous videos. So in the next pages you got description about those contact pins, which is not interested for programming. This diagram shows internally the memory is organized into three types: the main memory, the protection memory, and the security memory. And as you can see here, the protection memory is only for the lower 32 bytes. And these two blocks here, they says all the three types of memories are addressable and writable. So you can see that the address and the data bit over here. And this diagram also mentions about the same thing. It says the read is possible without authentication or pass verification, whereas the write has to go through the security logic. After this, the write is possible for the protection memory as well as the write for the main memory. And a couple of interesting points to remember in this paragraph here. So the interesting bit is the way the read and write, or the way the write is done to the memory. So whenever we write to the memory is erased, and then logically its logical AND operation happens as well. So the interesting bit here is it says all 8 bits of data, when erased, all 8 bits of data are set to logic 1. So this is something which is different when compared to other memory, where we always say that when memory is erased the data will be 0, but whereas in this case it is 1. So it also speaks about how the write is done. If it always happens by comparing the data already in the memory with the data we are going to write. If there is no difference, no write happens. If there is a difference, first the erase happens, then the logical AND operations will set any bits to zeros. So next here we got something about again same thing. 4442 mentions about the 4 bytes in the security memory, where the first 3 bytes are the top 3 bytes are the programmable security code, and the first byte is the error counter, that's called EC. And again here in the transmission protocol it speaks about the 4 different types here: the reset and answer, the command mode, the outgoing data mode, and processing mode. These all the 4 things are explained in later. So in the reset, see, whenever this is the device, the chip is powered, so it generates a ATR. So the documentation says the first 4 bytes of the memory is nothing but the ATR, and later in the document it explains what exactly these ATR bits are. So we are going to see this when I show you this the mapping between this document with the ACR 39X. And for the developers, these diagrams may not be of interest, and if somebody want to design a read-write chip or read-write circuit, probably they'll be interested in these diagrams. So what it also says here is, after the answer to reset, the chip waits for a command. So after that, only thing interesting bit here is every command includes 3 bytes. Okay. And next we got the outgoing data mode. So this is similar. This is same as the read operation, and the processing mode is same as the write operation or the compare or verification operations. So this is the structure of the command. So every command has got 4 bytes: the byte 1, the byte 2, and the byte 3, where the byte 1 is the control byte that indicates the type of the operation, and the second byte is the address, and the third byte is the data. And these are the different types of different operations or commands that are supported by this chip. So as you can see here, there is a read main memory operation. So in order to read, we have to specify the command byte, which is if you convert this into hex, you will get 30, and the address here. And when you do the read operation, we don't specify the data, so looks like whatever you put here doesn't matter. The next thing is the update main memory. So here also we got the command code that says this will be something like 38. You have to pass the address and the input data. Looks like you can write only 1 byte at a time. And the next command will be the read protection memory. So here we don't have to specify the address and data. So even though the address and data are not mentioned here, but the command must always be 3 bytes. So maybe you can put any values for address and the data. And the next command is the write production memory. So here also you have to specify the command. The command is 3b, and you got address and the input. So this is pretty interesting here, because so the write production memory, we always think that we just had to specify address and whether to lock or unlock, but the way the production memory works is different, which is described in later pages. And we also have for 442 we have got read security memory, this one. So where we just have to give the command code, and it reads all the 4 bytes. And next we have got update security memory. Here also, even though we know that the security memory has got 4 bytes, where the first 3 bytes are PSC, and this one is the error counter. So you can write 1 byte at a time. And the last one is the compare verification. Again, even though you have to compare the 3 bytes, you're going to compare byte by byte, which is explained in the later pages. So this section explains how the read memory operation works. So as you can see here in this section, so the main memory, protection memory, and security memory all starts with the same address 0. So address 0 for main memory corresponds to this byte. The address 0 for protection memory corresponds to a bit. This bit corresponds to the address 0. This bit corresponds to this address 1. And in the security memory side, the same address 0 corresponds to the error counter. So this is very interesting here as well. And the other thing to keep in mind here is, so to read the memory we specify just a single address, and every byte after this single address is read. So that's what is explained in this section. So here we got explanation about the read protection memory. So when you specify just the command, all these 32 bytes are read. So here the update main memory, so you can update 1 byte at a time. So that's what the command explains here. So here writing to protection memory. So the way the protection memory is locked, the way it's done is a bit interesting here. So it is not as simple as writing a 0 for a protection memory. So like write address 2 to 0. It's not like that. The protection memory is set, or the protection bit is set by comparing the data already in the memory and the data we specify in the command. Take for example, this is the memory address, say memory address 21. The data was FE. So if I have to log this address 21, the command will have the address 21 and some data. Okay, if these two data is compared by the chip, so if this comparison matches, only then the protection bit is set to 0. Keep in mind here the logic works in a different way. So 0 means protected, 1 means not protected. So here the memory protection works by comparing the old data and the new data. So reading the security memory, as the document explains here, you cannot, even though you can read all the 4 bytes, but if the chip is not authenticated with the PSC code, the first three or the value of this PSC values will always be 000. However, the error counter byte can always be read. But once it is authenticated, you can also read the 3 bytes of PSC. So here what the description says here is, after the authentication you can change the value of the PSC code, but you have to do this byte by byte. So here, and also you can also write to the EC as well. So because here the document says the address starts from 00 to 03. So if I want to write to EC or the PSC 0 or the PSC 1 or the PSC 2, so you can write one at a time. So this section explains how the verification is done. So verification is done in a series of steps. First, it sets an empty bit in the error counter. Then it compares the 3 bytes, and if the comparison is successful, it will reset the error counter. So after that, I think these are the main operations. Okay, all these things has to be done one after another. So it will be difficult to do all these things without a proper library. So that's the reason why using ATR 39X makes all these operations just using a single command. So this interesting flowchart. So this is how the verification works. First, we have to read the EC error counter. If the error counter is 0, that means we have used all the wrong attempts. Otherwise, you just set one of the free bit to 0, compare all the 3 bits, and if the comparison is successful, you reset back to, or reset the memory or erase the memory, and after this you will have a successful authentication. So in the last section there is a description about the ATR, and as the documentation mentions before, the first 4 bytes of the memory is ATR. You can see this has got ATR header, the first 4 bytes, and after that you got ATR data, and this is in address 4, address 5, address 6 and address 7. ICM and ICT is what is been highlighted here. It says the IC manufacturer identifier, and ICT is the IC type, maybe the type of this SLE 4442. After that you got the directory data information, which is all explained here, and this is again a bit by bit decoding of the ATR. The first byte has got so many information here, and the second byte tells us what's the memory capacity, whether the read is to read to end or read with a defined length. We have seen this before. This chip 4442 is a read to end type of chip. So because the read operation, you specify just the address, not the length. And this is how the memory looks like. It has got 3 sections: the main memory, the protection memory and the security memory, and the remaining bits or pages all about the technical and signals. So okay, that's all about this document. Next we are going to see how this document, how all these operations are available or made available in ATR 39X, and how that easy to use these commands using those ATR API.